Imagine a city map where each intersection is a node, and every road that connects two intersections is an edge. Each road has a length or travel time that we write as a number called a weight. The formal problem asks, starting from a special node S, our home, what is the shortest total length we can travel to reach every other node? In graph theory language, we have a weighted graph G equals V, E W, where V is the set of vertices, places, E is the set of edges, roads, and W maps E to real numbers greater than or equal to 0, giving a non-negative number to each edge. The output is a function dist of V for every V in V that tells the minimum sum of weights along any path from S to V. If no path exists, we say dist of V equals infinity. This is exactly what Dijkstra's algorithm computes. A practical example is routing a delivery truck. Each road segment has a travel time, and we need the fastest route from the depot to every customer. Think of Dijkstra's algorithm like a treasure hunt, where you always walk to the closest unseen treasure first. The greedy choice means at each step we pick the vertex whose current known distance from the start is the smallest, and we never change that distance later. Why can we be sure this is safe? Because all edge weights are non-negative. If you have already reached a place with the smallest possible total distance, any other way to get there would have to add extra non-negative road lengths, making it longer. With a negative road, imagine a slide that pushes you forward. You could later find a shorter route, breaking the greedy rule. Therefore, Dijkstra works only when every road length is 0 or positive. For example, in a subway network where travel times are never negative, the greedy step always leads to the optimal next station. The algorithm works like this. Give every node a tentative distance, 0 for the start node S and infinity for all others. Put all nodes into a priority queue ordered by their tentative distance. While the queue is not empty, remove the node U with the smallest distance. For each neighbor V of U, edge U, V with weight W, do. If distance of U plus W is less than distance of V, then set distance of V to distance of U plus W and update V in the queue. When the queue is empty, distance of V holds the shortest path length for every V. Function Dijkstra open parenthesis G, S close parenthesis colon. For each vertex V in G colon, distance V becomes infinity. Previous V becomes undefined. Distance S becomes 0. Q becomes a priority queue containing all vertices keyed by distance. While Q not empty colons, U becomes extract min of Q, vertex with smallest tentative distance. For each edge U, V with weight W colon, alt becomes distance of U plus W. If alt less than distance of V colon, distance of V becomes alt. Previous of V becomes U. Decrease key of Q V alt. Return distance previous. The concrete example. On a tiny graph of 3 nodes, a dash B2, a dash C5, B dash C1, starting at A, the algorithm first settles a 0, then relaxes B to 2 and C to 5, extracts B2 next, relaxes C to 3, and finally extracts C3. The distances are optimal. Explanation. To show the algorithm always gives the right answer, we keep an invariant. When a vertex U is removed from the priority queue, the value dist of U is the true shortest path distance from the start to U. Base case, the first vertex taken out is the start S, its distance is 0, which is clearly minimal. Inductive step, assume the invariant holds for all vertices already removed. Let U be the next vertex extracted. All paths to U must go through some vertex that is already settled. Otherwise, the path would contain a vertex still in the queue with a larger tentative distance, contradicting the fact that U has the smallest key. Because all edge weights are non-negative, the shortest such path has length dist of parent plus weight of parent to U. By the induction hypothesis, dist of parent is already optimal, and we have relaxed that edge when the parent left the queue, so dist of U equals that optimal length. No later relaxation can make it smaller, because any later edge would start from a vertex whose distance is at least dist of U. Hence the invariant stays true, and when the algorithm ends, every vertex satisfies it, giving correct shortest distances. This proof mirrors the classic optimal substructure argument used in dynamic programming. The running time depends mainly on how we manage the priority queue. Extract min is done once for every vertex, big O of V operations. Decrease key or insert happens for every edge when we relax it, that is at most E times. If we implement the queue with a binary heap, each operation costs big O of log V, so the total time is big O of V plus E log V, which for dense graphs where E is approximately V squared is big O of E log V. Space usage is simple. We store the distance array, predecessor array, and the heap. That is big O of V memory, plus the graph itself, which is usually big O of V plus E. The priority queue analysis is the key. The heap lets us always pick the currently closest vertex quickly, and it lets us efficiently lower a vertex's key when we discover a better path. For instance, on a road network with 1 million intersections and 2 million roads, a binary heap implementation runs in roughly a few seconds on a modern laptop, while a naive linear search queue would take minutes. Explanation: different heap types change the constants in the time formula. Binary heap: easy to code, each operation big O of log n good for most cases, total time big O of open parenthesis V plus E close parenthesis log V. Fibonacci heap: more complicated, but decrease key becomes big O of 1 amortized, while extract min stays big O of log. And this reduces the overall bound to big O of V log V plus E. It shines when the graph is very sparse and has many edges, because the E term no longer carries a log factor. In practice, the overhead often outweighs the theoretical gain. Bucket Q parenthesized dials algorithm works when all edge weights are small integers bounded by a constant C. It stores vertices in an array of C times V buckets, giving big O of 1 insert, and extract min, and overall big O of V plus E plus C times V approximately linear time. This is excellent for road maps where distances are measured in meters, and the maximum road length is limited. Choosing a structure is like picking the right tool: a screwdriver open parenthesis binary heap close parenthesis. For most screws, a power drill open parenthesis Fibonacci close parenthesis for massive jobs, and a wrench open parenthesis bucket close parenthesis when the bolts are all the same size. Dijkstra works for many variants, but we must pay attention to special details. Directed graphs edges have a direction like one-way streets. The algorithm treats each directed edge separately, relaxing only from the tail to the head. The same greedy proof works because we never travel against the arrow. Zero-weight edges: they are allowed because they are non-negative. They behave like free shortcuts. The algorithm may pull a vertex into the settled set earlier, but the invariant still holds because adding 0 never makes a later path shorter. Disconnected vertices: if there is no path from S to some vertex V, its distance stays infinity. The priority queue will eventually empty without ever extracting V. The algorithm correctly reports unreachable. If negative weights appear, the greedy choice can fail. Think of a slide that quickly drops you to a lower distance after you have already left a vertex. In that case, you need Bellman-Ford or Johnson's algorithm instead of Dijkstra. Where do we actually use this algorithm? Navigation apps. Finding the quickest route on a road network: edges equal road segments, weights equal travel time. Network routing. Internet routers compute least cost paths for packets. The cost may be latency or bandwidth usage. Game AI. Characters need the shortest path on a map to chase or flee. Social networks. Measuring degrees of separation between people. Each friendship edge weight equals 1. Empirical tests show that on real-world road maps, millions of vertices, a binary heap Dijkstra finishes in seconds, while a bucket queue can be faster when road lengths are integer meters. When the graph is huge and edge weights vary widely, a Fibonacci heap gives a modest theoretical speedup, but often the simpler binary heap wins because of lower constant factors. Benchmarks also reveal that preprocessing, like building a contraction hierarchy, can make queries near instant, but the core Dijkstra algorithm remains the educational and practical foundation for all these advanced tricks.